Good morning, students. Today I am coming up with the fourth video, that is continue the syllabus ideal regenerative Rankine cycle. Today I am going to discuss ideal regenerative Rankine cycle, actual regenerative Rankine cycle, that is practical Rankine cycle, and also open feed water and closed feed water and reheat cycle. So just as what is the regeneration means what I have explained in the gas power plant, that is using heat from the main source only. We are not spending any extra amount or equipment or anything within the circulation only. If you just modify the path of flow, you can get the extraction of that heat, and which can be used in some other purpose to save the energy. So this just earlier it was like a boiler, turbine, condenser and a pump. Now I just modified and made this system like this. So this is the turbine, this is boiler, this is condenser and this is a pump. So we know that from boiler steam is passing through the turbine to rotate the blades and generate the energy. From that I'll just exactly pass through the center and I'll take that steam out at 2, and what I'll do is I'll just pass through the condenser. See, whatever input to the boiler is normal water, right? If I send a preheated water, that is means somewhat increased temperature water, so that boiler fuel consumption will be reduced. So what exactly we are doing is, usually after pump was directly supplying the water to the boiler, but modification what we did is just we pass this water through the casings of the turbine, because we know that we are supplying the superheated steam in the turbine, which is very high energy and high temperature. That temperatures are also transforming to the walls of the turbine. So one casing will provide, and this is a hollow casing. So here I am doing the input, here I am taking that output. 4 is coming at 4 dash out, means circulatory, this around this the steam is circulating and coming out, means turbine is already heated one, so that heat is taken out and that is coming at 4, and this preheated water is supplied to the boiler. So that, so am I spending any extra equipment or extra fuel for heating this feed water? No, just I am just passing this feed water in the casings of the turbine, and I am just taking out and passing to the boiler. So if I draw the TS diagram for this setup, so this is usually this 1, 2, 3, 4, 4 dash. Instead of 4 dash we were using 5, but here I am using 4 dash. 1, 2, 3, 4, 4 dash 1 was Rankine cycle. But in the casing, some of the heat is extracted, no, heat from the vapor, and this is heat from this water. So 4 dash will indicate regenerative heating, and 4 dash 1 will heat the feed water. This FW means feed water in the boiler. So this is how we can analyze regenerative, but ideally this is only ideal case. Practically this is not possible. Practical case we will discuss in the next video, this one next step. So but we will derive the efficiency for this cycle. So we know that from the entropy chapter in the basic thermodynamics, we know that Q is equal to TdS. Here also, since I have TS diagram, we will use TS diagram for calculating the heat supplied or rejected. I have already repeatedly saying that PV diagram will give you work done and TS diagram will give you heat supplied or heat rejected. So here I want only heat supplied and heat rejected. So heat supplied in the boiler is boiler is this part. So T1, temperature T1 into this one, entropy difference S1 into S4 dash. Heat rejected in the condenser here, S2 dash minus S3. So since path 1, 2 dash, this is coming like this is coming like, both are parallel. So parallel lines I will just take S4 dash minus S3, this S4 minus S3 difference and S1 and S2 dash difference, and just equate it because both are parallel having same this one numbers, ratio will be same. So just mathematical modification, I will take this side and I will shift this one. So S1 minus S4 dash and S2 dash minus S3. So it means whatever S2 dash, here I have written S2 dash minus S3, S2 dash minus S3 is equal to S1 minus S4 dash. So I can write QR is equal to T2 into S1 minus S4 dash because these two are equal. Now if I supply substitute in this equation, we know that efficiency is equal to 1 minus QR by QS. So QR is T2 into this one, T1 into this one. Both are equal, so they will get cancelled. So finally I got the equation 1 minus T2 by T1. So this is ideal regenerative cycle, but practically this is not possible. So reasons I just read out. Heat transfer in the turbine casing cannot be obtained in a finite time because within a time pump is pushing the water and the water is coming out within short period of time. I don't know how much heat is transferring. That is finite amount of heat will not find transfer in the this one. Heat exchanger in the turbine mechanically, it is mechanically impractical, right? So moisture content, so this will reduce the moisture, increase the moisture content in the steam. So again that will be having more and more problems. So as to overcome this, we'll have an actual Rankine cycle. I'll just draw it. This is a little bit big diagram. Just I'll draw, and please understand the concepts. So this is very important. Here only I will write actual. Normal figures. First I draw the turbine. Little bit bigger I will draw so that you can understand easily. So inlet to the boiler, from boiler to the turbine, first one. So here we can generate the energy, right? Now just follow this diagram. First I will explain. What I have drawn, just look at the diagram, right? One more similar thing I will draw. Just look at the procedure how I am drawing so that you will not get any confusion. This is exit of the turbine. So here we have condenser. From this I am taking out to the through the pump and just Just I'll draw the TS diagram also. And I'll name it first. This is 1, 2, this will be 3, this will be 4, this will be 5, this will be 6, this will be 7, this will be 8, this is 9, and this is 10. See, earlier what we have done in the ideal Rankine cycle, we have passed the steam in the casings, but that is not practical. But here we'll see, look at the practical one. So actual Rankine cycle, what we are seeing here is from the turbine. There are so many stages will be there in the turbine. From first stage where bleeding, it is called as bleeding, means taking some m1 kg of steam. Some second stage I am taking m2 kg of steam, and remaining is coming out at the outlet. Right. First we'll see boiler is producing the steam, steam is supplied to the turbine. Right. And it is going first, it is coming out. Right. So first remaining amount of this one steam, whatever it is coming, this one we are passing through the condenser, this is pumped back to the liquid. But directly earlier what we used to do, condenser output through the pump it was supplied to the boiler. But now what I will do, I will pass to the low pressure heater, LP heater. So this water and this m2 kg of steam whatever, when I say m2 kg, it is little bit wet steam that will be coming out, and this in LP heater, this m2 kg steam is having some amount of temperature that will pass to this water from the condenser, and this will reduce this temperature and this will get heated, means both will mix and come out as a liquid with certain increased temperature. Right. So here what is the aim of this regenerative Rankine? To heat this output of the condenser and give a feed water with a increased temperature. See here, if I am supplying normally, if I am supplying 25 degrees Celsius of water, and with this setup if I supply 90 degrees Celsius of water, then it will be helpful for us to consume very less fuel to increase. So it has reduced some 65 degree temperature rise, it has reduced the fuel consumption. So this will be helpful. Now this I am here 1 minus m1 minus m2 kg of steam, that water is supplied to this low pressure heater and it is mixed with m2. So when this is added to this will become 1 minus m1. It will come out as 1 minus m1. Just add 1 minus m1 minus m2 plus this m2 is adding here. So this and this will get cancelled, 1 minus m1 will remain, and practically it is possible. So this is how it is coming here. Then again pumping and passing to the m1 kg of steam. m1 kg is again more heated. Suppose if I have some 30 degrees Celsius, here it may increase up to some 40, here it may increase up to 90 degree. Example, it is not as practical. Right. So here it is passing through low pressure. Again from this pump I am not supplying directly to the boiler, I am just supplying to the high pressure heater. So high pressure heater, here what all things are mixed, 1 minus m1 and plus m1. So I am getting 1 kg. Here what, how much I supplied, just say 1 kg steam I have supplied, I am getting back 1 kg of water, feed water. Here it is called as feed water. Right, and these HP and LP heaters are feed water heaters. From this again I am supplying to the boiler. So what is its help you got now? Because to increase the feed water temperature we are doing the regeneration. So this method is helpful. If I pass this in the casing, it is practically not possible. But taking out the steam and heating the condenser output, then it is possible. Right? Just I'll plot a TS and HS diagram for this. Just look this. 1, 2, 3, 4. 4, 5, 6, 7, 8, 9, 10. So this is our 10. 10 and 11, sorry, here it is 10 and it is 11. 11 is at boiler, right? And HS diagram, just I'll plot. This is HS diagram, you can see in the Molière chart. It is a saturation line, and from here, this is the saturation line, and here T superheated will be going out, and this one is just I'll draw the constant pressure lines. And if suppose I have P1 here, will go on reducing like this in a straight line because it is isentropic we are assuming. P2, P3 and P4. So here P1 it is 1 kg directly we are getting at 11, yes or no? And at 2 how much we are getting? M1 kg. At 2 M1 kg. Here it is 2. At 3 M2. M2. And here M1 1 minus M1 minus M2 kg. What is pressure here? P4. Pressure is P3. Pressure is P2. Here pressure is P1. See, just look here. 1, 2, 9, 10, 11. 1, 2, 9, 10, 11. This will complete one cycle. Again, 1, 3, 7. 1, 3, 7, 8, 9. Correct. Here only it will join this earlier. So here 1, 3, 7, 8, 9. Again it will join this. Here again 1, 4, 1, 4, 5, 5. It is coming like this. 6 and 7. 6, 7. So this is how the TS diagram. Right. So whatever explained I have given in the notes already. It is with me in the PDF form. So now I'll just write the heat supplied equations and this one heat added, heat rejected. Right. Just shall I rub this? I'll rub this here because I can use the diagram again. So isentropic turbine work. I'll just write directly turbine work. Pump work is not required here, so that is neglected. Heat added and heat rejected. So WT, QS and QR. So turbine work, just look here. First 1 kg I am supplying, 1 kg mass into H1 minus H2. Here some of the expansion is happening because here it is coming out, it is going out. Next one more is plus 1 minus M1 is remaining there because 1 minus M1 is going from here at this point after bleeding. What is the this one? H2 is the enthalpy in inlet and H3 is the outlet, plus 1 minus M1 minus M2 is going out, and H3 minus H4. This is the work done by the turbine. Right. So what is the heat supplied? Simple. Heat supplied is 1 kg we are getting. Here also 1 kg, here also 1 kg. Heat supplied is at the boiler. How much it is? H1 minus H9, because we are neglecting pump work and everything. So directly from here only in here, high pressure heater heat is supplied. So H1 is the amount of heat gained and it is inlet heat. So this much is the difference is heat added. Heat rejected, heat here also heat added, heat is also heat added, here also heat added, heat rejected is only at the condenser. So how much it is? 1 minus M1 minus M2 into H4 minus H5. H4 minus H5. So thermal efficiency I can write like this: neta regenerative is equal to 1 minus this one W net, W net by QS also, or you can write QR by QS also. So QR by QR is 1 minus M1 M2 into H4 minus H5 divided by QS is H1 minus H9. So this is what is the efficiency of regenerative cycle.